Welcome everyone. Today, we are looking at topic 5 in your SS3 physics series, Wave-Particle Duality. This is an introduction to quantum physics. It is a fascinating topic that reveals the strange behavior of light and matter. This topic is regularly tested in your examinations. You must understand the key concepts and experiments. Pay close attention. Let us begin. First, let me explain what wave-particle duality is. Wave-particle duality is the concept that every quantum entity, such as light and electrons, exhibits both wave-like and particle-like properties. This is a fundamental principle of quantum mechanics. It means that light can behave as a wave in some experiments and as a particle in others. Similarly, electrons can behave as particles in some experiments and as waves in others. This duality is one of the most important discoveries in physics. It changed our understanding of the nature of reality. Understanding wave-particle duality is essential for understanding quantum physics. This is the foundation of modern physics. Now, let me explain the wave nature of light. Light was first understood as a wave. This was based on the work of scientists like Huygens and Young. The wave nature of light is demonstrated by several phenomena. The first is interference. Light waves can interfere constructively and destructively. The double-slit experiment is a classic demonstration. The second is diffraction. Light waves spread out when they pass through an opening. The third is polarization. Light waves can be polarized, which is a property of transverse waves. The fourth is reflection and refraction. Light waves obey the laws of reflection and refraction. Understanding the wave nature of light is essential for understanding optical phenomena. This was the classical view of light. Now, let me explain the particle nature of light. The particle nature of light was established by Einstein. He explained the photoelectric effect using the concept of photons. A photon is a particle of light. It is a quantum of electromagnetic energy. Photons have energy and momentum. The energy of a photon is given by the formula E equals h times f. Here, E is the energy of the photon. H is Planck's constant. F is the frequency of the light. Planck's constant is 6.63 times 10 to the power of negative 34 joule-seconds. The momentum of a photon is given by the formula P equals h divided by lambda. Here, P is the momentum. H is Planck's constant. Lambda is the wavelength. Photons travel at the speed of light. They have no mass. Understanding the particle nature of light is essential for understanding quantum phenomena. This is a key concept in modern physics. Now, let me explain the photoelectric effect. The photoelectric effect is the emission of electrons from a metal surface when light shines on it. It was discovered by Hertz. It was explained by Einstein. The photoelectric effect demonstrates the particle nature of light. There are several key observations. First, electrons are emitted only if the frequency of the light is above a certain threshold frequency. Below this frequency, no electrons are emitted, regardless of the intensity. Second, the kinetic energy of the emitted electrons depends on the frequency of the light, not the intensity. Third, the number of electrons emitted depends on the intensity of the light. Fourth, the emission is instantaneous. There is no time delay. Understanding the photoelectric effect is essential for understanding quantum physics. This is a frequently tested topic. Now let me explain Einstein's explanation of the photoelectric effect. Einstein proposed that light consists of packets of energy called photons. Each photon has energy equal to h times f. When a photon strikes a metal surface, it transfers its energy to an electron. The electron uses some energy to overcome the work function of the metal. The work function is the minimum energy required to remove an electron from the metal. The remaining energy becomes the kinetic energy of the emitted electron. The formula is E equals h times f equals phi plus 1/2 times m times v squared. Here, E is the energy of the photon, is Planck's constant. F is the frequency. Phi is the work function. 1/2 times m times v squared is the kinetic energy of the electron. This equation explains all the observations of the photoelectric effect. Understanding this explanation is essential for understanding quantum physics. This is a key concept. Now, let me explain the work function. The work function is the minimum energy required to remove an electron from the surface of a metal. It is denoted by phi. It is measured in electron volts or joules. Different metals have different work functions. Sodium has a low work function. Tungsten has a high work function. The work function depends on the metal's atomic structure. The threshold frequency is the minimum frequency of light required to emit electrons. It is given by F subscript naught equals phi divided by h. Below this frequency, no electrons are emitted. Understanding the work function is essential for understanding the photoelectric effect. This is a key parameter in quantum physics. Now let me explain the wave nature of particles. De Broglie proposed that particles also have wave properties. This is called the de Broglie hypothesis. He suggested that matter has wave-like behavior. The de Broglie wavelength of a particle is given by the formula lambda equals h divided by p. Here, lambda is the de Broglie wavelength. Is Planck's constant. P is the momentum of the particle. This means that every moving particle has a wavelength associated with it. The wavelength is inversely proportional to the momentum. Massive particles have very short wavelengths. Light particles have longer wavelengths. Understanding the wave nature of particles is essential for understanding quantum physics. This is a fundamental concept. Now, let me explain the experimental evidence for the wave nature of particles. The wave nature of particles was confirmed by the Davison-Germer experiment. In this experiment, electrons were fired at a nickel crystal. The electrons were diffracted by the crystal. This produced a diffraction pattern. Diffraction is a wave property. This experiment confirmed de Broglie's hypothesis. Electrons behave as waves. Similar experiments have been done with neutrons and atoms. All particles exhibit wave-like behavior. The wave-particle duality is a universal property of matter. Understanding this experimental evidence is essential for understanding quantum physics. This is frequently tested. Now, let me explain the double-slit experiment. The double-slit experiment is one of the most important experiments in physics. It demonstrates wave-particle duality. When light passes through two slits, it produces an interference pattern. This shows the wave nature of light. However, when light intensity is reduced so that only one photon passes at a time, the photon still produces an interference pattern over time. This shows that each photon behaves as a wave. If a detector is placed at the slits to determine which slit the photon passes through, the interference pattern disappears. The photon behaves as a particle. This experiment shows that the act of observation affects the outcome. Understanding the double-slit experiment is essential for understanding quantum physics. This is a mind-bending concept. Now let me explain the complementarity principle. The complementarity principle was proposed by Niels Bohr. It states that wave and particle aspects are complementary. They are not contradictory. They are two sides of the same coin. The wave and particle nature of matter are mutually exclusive. In any given experiment, only one aspect can be observed. For example, the double-slit experiment demonstrates wave nature when interference is observed. It demonstrates particle nature when the path is detected. Both aspects are necessary for a complete description. Understanding the complementarity principle is essential for understanding quantum physics. This is a key philosophical concept. Now, let me explain the uncertainty principle. The uncertainty principle was proposed by Werner Heisenberg. It states that it is impossible to know both the position and momentum of a particle with unlimited precision. The more precisely you know the position, the less precisely you know the momentum. The more precisely you know the momentum, the less precisely you know the position. The formula is delta x times delta p is greater than or equal to h divided by 4 pi. Here, delta x is the uncertainty in position. Delta P is the uncertainty in momentum. Is Planck's constant. This principle is a fundamental limit of nature. It is not a limitation of our instruments. It is a property of quantum systems. Understanding the uncertainty principle is essential for understanding quantum physics. This is a key concept. Now let me explain the applications of wave-particle duality. Wave-particle duality has many applications. In electron microscopy, the wave nature of electrons is used to image very small objects. Electron microscopes have much higher resolution than light microscopes. In quantum computing, the wave and particle nature of quantum bits is used for computation. In medical imaging, X-rays and gamma rays are used for diagnosis and treatment. In solar cells, the photoelectric effect is used to convert light into electricity. In spectroscopy, the wave nature of light is used to study the composition of materials. Understanding the applications of wave-particle duality is essential for understanding modern technology. This is a key topic in physics. Now, let me explain the importance of wave-particle duality. Wave-particle duality is important for several reasons. First, it is the foundation of quantum mechanics. It explains the behavior of atoms and subatomic particles. Second, it explains the photoelectric effect. This is essential for solar cells and photodetectors. Third, it explains the wave nature of matter. This is essential for electron microscopy and quantum computing. Fourth, it challenges our classical understanding of reality. It shows that the universe is strange and counterintuitive. Fifth, it has led to many technological advancements. Understanding wave-particle duality is essential for physics and technology. It is one of the most important concepts in modern science. Now, let me give you sample exam questions to prepare you for your test. What is wave-particle duality? Wave-particle duality is the concept that every quantum entity exhibits both wave-like and particle-like properties. Explain the photoelectric effect. The photoelectric effect is the emission of electrons from a metal surface when light shines on it. State Einstein's photoelectric equation. E equals h times f equals phi plus 1/2 times m times v squared. What is a photon? A photon is a particle of light, a quantum of electromagnetic energy. State the de Broglie hypothesis. The de Broglie hypothesis states that matter has wave-like properties. State the de Broglie wavelength formula. Lambda equals h divided by p. Explain the uncertainty principle. The uncertainty principle states that it is impossible to know both the position and momentum of a particle with unlimited precision. What is the complementarity principle? The complementarity principle states that wave and particle aspects are complementary and mutually exclusive. Let me summarize everything we have covered today. Wave-particle duality is the concept that light and matter exhibit both wave-like and particle-like properties. Light behaves as a wave in interference and diffraction. Light behaves as a particle in the photoelectric effect. Photons are particles of light. The photoelectric effect is explained by Einstein's equation. De Broglie proposed that particles have wave properties. This was confirmed by electron diffraction. The double-slit experiment demonstrates wave-particle duality. The complementarity principle states that wave and particle aspects are complementary. The uncertainty principle states that position and momentum cannot be known precisely. Wave-particle duality has many applications in modern technology. Understanding wave-particle duality is essential for physics and technology. This is Topic 5 in your SS3 Physics series. Study it well. It is regularly tested in your examinations. Well done.